Hi, in this video, we want to take a first look at multiple linear regression. All right, so up until now, we've been looking at linear models where we have one target variable and one predictor. What we're going to do this time is that we still have one target variable. This is the one we want to predict or make an inference on, but we have a bunch of predictor variables. All right, so things are going to be a little bit more complicated, but conceptually, everything's going to follow what we've already talked about. Okay, so one thing that's going to become an issue is that, previously when I had a target variable and one predictor variable, my choices were use the model or don't. Like that one predictor variable was it. Either I went with it or I didn't. Now it's more complicated because I've got multiple variables. Do I want to use all of them? Should I add one more? Should I remove one? We have to make a decision. And what we want to be able to do going forward is be able to figure out which variables, if any, should be included. Okay, so let's go ahead and load some data. So what we're going to do, we're going to take the NYC data set from the textbook's website. And one thing I'm going to do, right, so I am reading a CSV, read.csv, because that's how it's stored. You notice I've got strings as factors equals false. Okay, so by default, R will load, if I use read.csv, it will load character strings as factors. And that kind of makes sense, but factors are kind of difficult to work around. So my advice to you, anytime you have nominal data, ordinal data, load it as a character string, and then later on in your process, then start setting things up to get things the way you want it to be when it comes to the factors. After you've cleaned up the text, after you've made things more uniform, after you understand what's going on. But that's something that I kind of learned the hard way. So my advice to you, initial load, when you first start working with a data set, always go with character strings and don't load anything as factors. Now, right here, I'm going to change the row names to the restaurant name. Why do I do that? All right, so think about all those diagnostic plots that we were looking at previously. Well, whenever a diagnostic plot flags an observation, it labels it with the row name, right? Okay, so if I leave it on the default row name, it's going to say 2 for like row 2, 5 for row 5, 10 for row 10. Remember, by default, it labels 3 on each plot. Well, does that really tell me what I'm talking about? No, I'm talking about restaurants, right? I can go ahead and just put down the restaurant's name, and I know which restaurant I'm talking about. So I'm going to go ahead and change the row names to the restaurant. Okay, let's keep on going with this. And hopefully by now, you know that I like to color my plots in a way that corresponds to the target variable. And that's what I'm doing here. So I'm going from the minimum of the target variable to the maximum from min to max by 1. Then I'm getting a color for each distinct value in the Viridis color palette. So I'm saying n equal to the length of this vector that I've defined. And then I'm setting the names to the sequence of values, and then I just pass the target variable as a character. So why do I do this as character business? Well, when I do a name, this statement right here, I'm taking the values that we have, like the range of values that we could potentially have for the price. Well, I'm going from the minimum value to the maximum value, and I'm setting them as names. Well, if they're names, they become character strings. As they become character strings, when I grab my target variable, I need to set as.character. What will happen if I don't? Well, if I see a 5 in my target variable column and it's a number 5, it's going to say the 5th row. Instead, I want character string with parentheses 5 instead. So I need to do this. I need to do it this way. So I go ahead and color it like that. All right, well, now I've got multiple values. And I want to go ahead and visualize what's going on. So I've got multiple predictor values. Now, what was I doing previously? I was doing a scatter plot. My most important plot when I do multiple regression, when I do regression period, is the scatter plot. Now, a scatter plot takes two variables. Okay. Well, do I want to go through and take the first predictor and the second predictor, third predictor, and make a whole bunch of scatter plots? Yes, I do, but I want to do it efficiently. So to do it efficiently, I'm going to do a pairs plot. All right, the pairs plot, what it's going to do is it's going to take the data set and it's going to make a scatter plot for every pair of columns that I have. And so my model that I'm going to be working with ultimately, so I already worked out that some details and I went back and put this in afterwards. So it's a little bit cleaner for you to watch, but we're going to have price depends on food and decor and service and east or west location. The data is from NYC. The color is from the color field that we already defined up here. And then I'm just going to use that solid plot character. So let's take a look at what this looks like. All right, so we can see that this row is price. This column, it also has price. This row has food. This column has food. This row has decor. This column has decor. This row has service. This column has service. And this row has east, and this column has east. So what's going on here? This is the scatter plot of price on the y-axis, food on the x-axis. Over here, this is the scatter plot of price on the y-axis, decor on the x-axis. Down here, this is the scatter plot with decor on the y-axis and service on the x-axis. All right, because you can see service is below, so it goes along the x-axis. Well, what if I go down here? If you look at this for a bit, you'll realize that these look similar, but there's kind of like just reflected. What's going on here is that service is the y-coordinate and decor is the x-coordinate down here. So this plot and this plot are actually the same. There's just a there's just a reflection on the axes. This plot and this plot are the same. This plot and this plot are the same. Price and service, price and service. Now, when I look at east, I notice that east only has two values. And since it only has two values, then this scatter plot really doesn't tell me what I'm looking for. I'm going to go ahead and use a box plot on the east data like that with price and east. And I'm not going to go ahead and bother with all the other predictor variables because price is really the main one. If I wanted to go deeper, I would go ahead and get the price, or I would get east with the other variables, but this is going to be good enough for us. So what I'm going to do, I'm going to make a box plot. And I find that steel blue prints very well on paper. Like printers tend to make the color look pretty well. It doesn't get degraded too bad. And I like the color. So I went ahead and went with that. Now, something I'm going to do, I'm going to go ahead and use that rug command to put a little tick on the side axis of the visualization. And so on one side, whenever east is equal to 0, that is, it's west, then I'm going to put it on side 2. And when east is equal to 1, it's east. I put it on side 4. Okay, so in R, side 1 is down, side 2 is to the left, side 3 is up, and side 4 is to the right. I didn't point left and right because I'm on my laptop, it's reflecting. I'm not 100% sure which way it's recording my image. So I don't know which way is left or right from your point of view. So I'm just not going to do it. Okay, so let's take a look. So we can see that the median of the price when east is equal to 1 is a little bit bigger, but not a lot bigger. So we can see that the median lines intersect vertically with the other boxes. So I'm not seeing a big difference between east and west. East might be a little bit bigger, but who knows? Now, you'll notice that I used the jitter function over here. So what this does, jitter adds a little bit of normal distribution noise to shake things up, to move things about. Why did I do that? Well, in the original version of the rug command, the values were stacked on top of each other. So if I had a particular value of price, and I see it 5 times, it's like 1, 2, 3, 4, 5, and they stack. and I can't see all of them. To be able to see a little bit more, I kind of just bump it a little bit, and we end up seeing it gives a better representation. So we can see that there's a good amount of points here. It actually goes a little bit above the box, a little bit above the top edge of the box, a little bit of, this is above the lower edge of the box, and we can kind of get a feel for where the observations are. All right, so now let's go ahead and do a linear model. I'm going to call it linear model 4 because we have 4 predictor variables. So price depends on food, decor, east, and service. Now, something that is important that's going to come up in a moment, the order of this will actually impact some of our hypothesis testing down the road. Initially, it's not a big deal, but when we get deeper into this, order of the predictor variables is important. Okay, so the summary command evaluates if a coefficient is equal to 0 or not in the hypothesis testing. So if I look at food, here is its estimated coefficient. And I can see the p-value is pretty small, so it's statistically significantly different than 0. And here we've got decor, east, and service. The service is coming kind of, it looks like that might be equal to 0, which was consistent with the box plots. All right, so the summary command, it's evaluating the hypothesis test that the coefficient is equal to 0. Order does not matter on this test. And we can take a look at our multiple R squared and our adjusted R squared. Now, something that is important for us is that if I have like junk predictor variables, or I have too many predictor variables, I can do what's called overfitting. And overfitting is a problem. Just like the name says, it says overfitting. That means I'm overdoing something. Well, one of the first things you want to do to check is that you want to see, does regular R squared and adjusted R squared, are they close to each other? If they're close, then then that's one of the things to signal to me that it's not too bad. As these values get farther and farther apart, I get more worried. That's my first look. These are pretty close. I mean, 0.63, 0.62 after rounding. Yeah, I'm not worried about it. Adjusted R squared will be smaller, by the way. All right, so now let's do Anova. Now, Anova, what it's going to do, it's going to evaluate a hypothesis test for each of the individual coefficients, seeing if it should be added to the model or not. And of course, I want to do my diagnostic plots. And you'll see once again, I'm setting the color to the background, and I'm plotting with plot character 21. That gives me a black dot with a colored center, and the color corresponds to the colors I already defined. Let's go through. All right, so first thing I want to jump out at you is that you see that the names of the restaurants that have high residuals, the three largest residuals in magnitude, are plotted right away for us. So we can initially see, hey, there might be something going on with those individual restaurants. By changing the row names like I did, I know which restaurants those are right off the bat. And I've got my normal plot, just like before. And this is pretty close. I mean, this part could be a little bit closer to the line, but honestly, that's pretty darn good. Probably not going to see better in real life, at least. All right, so once again, we see the Nello is coming up. There's something with that Nello observation. Don't really know what yet, but something's going on. Here's the square root of the standardized residuals, plotted by the FID values. All right, we're looking at Cook's distance on this one. Once again, Nello comes up. Someone's up with that restaurant. Maybe we shouldn't eat there. Maybe there's something wrong. Or maybe it's so great that that's why it's an outlier. Who knows? Who knows? All right, so here we've got residuals versus leverage. And these plots should feel familiar to us at this point, like we've already seen these plots, because these are the same ones we've been looking at so far. And we've got our Cook's distance versus leverage. Okay, well, if I go back up and I look at the summary, I can see that, well, actually, I'll do summary and Anova. If I look at the summary, I can see, look, service is, I cannot conclude that the service coefficient is not 0. I mean, the magnitude is close to 0. The standard error is big enough that the p-value is super big. I fail to reject the null hypothesis. I conclude that service is actually equal to 0. Well, if it's equal to 0, that means I don't want it in the model. I want to remove it, make things less complicated. So what I'm going to do, I'm going to use the update function to remove the variable that I don't want. So you'll notice the formula is just a tilde dot, then I subtract off the variable I want to get rid of. I have the object is the model, and then I just subtract what I don't want. Boom, you got it. All right, so now let's take a look. What do we get? And you'll notice that the p-values change whenever I remove a variable. That's going to be an important concept later. So here is my linear model, or how I call it at least. And all of the variables are statistically significantly, different from 0. The R-squared and adjusted R-squared are pretty tight. That's good. F-test makes me feel good about this model. All right, all right. Now let's do the Anova. And things are pretty consistent on the Anova front. Okay. Now, something that we need to think about when we talk about Anova is that Anova always compares at least 2 models. Anova always compares at least 2 models. But we've been doing Anova so far. Well, you're comparing the null default model, which is the constant model, no variables, compared to the model that you're dropping in. So here, when I run this command, I'm comparing LM3, a linear model with 3 predictor variables, to the linear model that's just constant. Like, the average of price is my linear model. There's no predictor variables involved. And it's comparing the two when it performs all of these calculations. When I come down here, I'm comparing linear model 4 to linear model 3. All right, what this is doing is this is asking, is that extra variable in linear model 4, is that worth keeping? Okay, so the null hypothesis is that these 2 models are equal in all, or these 2 models are equal in informative value. That's probably the best way to word it. These 2 models are equal in informative value. Okay, if 2 models are equal, one is simpler than the other, then I want the simpler one because it's easier to work with, easier to interpret, easier to do calculations with. Okay, so if I reject the null hypothesis and I conclude that these 2 models are equal, then I'm going to go with the simpler one. If I conclude that the 2 models are not equal to each other in informative value, I'm going to use the one that has the other variable in it. So let's take a look. I can see I get a p-value of 0.99. Whoa, 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 we failed to reject the null hypothesis. Null hypothesis is that the 2 models are equally informative. So I have one with 4 variables and one with 3. Which one's simpler? 3 variables. So what I would conclude from this hypothesis test is that the linear model with only 3 predictor variables is actually the better one to use. Okay. So let's go ahead and plot. And once again, Nello's coming up. Something interesting. I think the word rainbow is in there. The Nello, I think that's rainbow. Yeah. Things look pretty similar, which is not all that surprising. Okay, now I told you that we have different kinds of ANOVA. When we start doing multiple linear regression, we have tons and tons of different hypothesis tests that we can run to get an inference. The summary function evaluates the hypotheses that the different coefficients are equal to 0, and it does it individually for each coefficient. Now, ANOVA compares models to each other. And there's always at least 2 models in a ANOVA test, whether we say one is in there or not. If we just put in one, it always checks the constant value model against it. So what we're going to do, for ANOVA, order of the predictor variables matters. So I'm going to make linear model, decor, food, east, service. You see how I have the predictor variables in that order? Decor, food, east, service. When I get to here, I'm going to go service, east, food, decor. I've got the same variables as the predictor variables, but I've got them switched in the order because I want to show that we're going to get different p-values. We're going to get different statistics when we do our ANOVA test. Okay, so when I go decor, food, east, service, and I run the model, you can see that service is definitely not statistically significant. But let's look real quick. Excuse me. All right, so if we look here, let's look at, let's say, decor. Decor is 1.9 e to the negative 15, 1.9 e to the negative 15. Decor is, all right, that's the same. Oh, it's rounding off, isn't it? Oh no, oh no. You can't see the difference because it's rounding off. Ah. Okay, well, they're going to be different. All right, so let's look at actually the t-values. Okay. Oh, actually, so, I'm sorry. We're in summary. I was thinking we were in ANOVA. All right. So if we look through, we can see, as I was just bouncing back and forth aimlessly, that all of these values are the same regardless of the order. So summary, it doesn't matter the order of the predictor variables. In summary, it doesn't matter what the order of the predictor variables are. But when I get to ANOVA, it does matter. So let's scroll down. All right, so let's take a look at this real quick. Let's scroll down. All right, so when I looked at this, okay, so food had an F value of 40.31. Here, food has an F value of 16.23. And the p-value is 2.1 e to the negative 9. Here, the food value is 8.6 e to the negative 5. When I look at east is 0.028. Here, east is 0.26. Oh, that's a big difference. All right, so what this is doing is that this is evaluating if, let's say I start out with the default model, the constant model. Should I add decor to the constant model? Yes or no? That's what this test is doing. Now, when it looks at food, it's considering, okay, I have decor as my one predictor. Should I add food to the one predictor model with decor? Should I add it, hypothesis test, yes or no? When I look at this line is asking, should I add east to the model with decor and food? And when I look at this model, this is asking, should I add service to the model with decor, food, east? Right, so think about it. The order matters when I articulate it this way. When I come down here, this is the hypothesis of, should I add service to the constant model? Here, I'm asking, should I add east to the model with service and a y-intercept? This is asking, should I add food to the model with service and east? This one is asking, should I add decor to the model with service, east, and food? So the order of this matters. So that's something that's very important when we interpret this. There are 3 types of sum of squares to be working with. Summary gives one type, this Anova gives another, and the naming criteria or the naming convention for Anova is established by SAS. SAS is really the first ones to like iron out a lot of these details. There's type 1, type 2, type 3. All right, that's all I've got for you. Take care and goodbye.